Hi Calc students, this is video 5-2 for Wednesday, January 4th, 2017. Today we're going to estimate the area under a curve using trapezoids. This will give us a better approximation than the rectangles. And so to do what we're doing today, we need to know the formula for the area of a trapezoid. So the area of a trapezoid is 1/2 base 1 plus base 2 times h. So here's an example of what it looks like to estimate area with trapezoids. All of these are trapezoids, but something important to note is that if these were rectangles, this would be the base. But for trapezoids, this is actually going to be the height. Your delta x will be the height, because if I turn the paper around like this, you can see that this is a trapezoid. So base 1 and base 2 are going to be given by the function values we get from plugging in the endpoints, and then the height is going to be the delta x. Okay, so it's a little bit different that way. Just remember that the trapezoids are on their side. That might help you. Okay, so for this problem below, use the graph to approximate the area, A. So they mean all of this area. And round your answer to 3 decimal places. So they're not being super specific about, the interval or the subintervals, but I think it's pretty clear that we're on 0 to 6. And we have 1, 2, 3, 4, 5, 6 subintervals that we're using. So let's look at our first trapezoid. So this is the height of our first trapezoid, right? Remember, because it's on its side. And then when you do the bases of a trapezoid, that's how you're going to get them, by getting the function values at either endpoints. So you have to go to the left endpoint and up to the graph, and to the right endpoint and up to the graph. So those are the bases. So this is the height of the trapezoid. Those are the bases of the trapezoid. And then to get the other leg of the trapezoid, the slanted leg that won't give you the height, you just connect the points on the graph like that. Okay, so there's the first trapezoid. The second trapezoid, there's its base. We already drew, no, I'm wrong. There's its height. We already drew one of its bases, then the other base will be coming off of that end. So there's the second trapezoid. I'm going to not use a ruler. I recommend using one, though, because it will look better, but just in the interest of time, I'm not going to. All right, this is our, so a trapezoid is a rectangle, you see. Like that's a fact. So now this next part, we've got this height of the next trapezoid. We already drew base 1. Now this will be base 2. That's base 2 of the third trapezoid. And then you just connect like that. All right? And you can already see the trapezoid is going to more closely follow the edges of the curve, better than the rectangle. So these will give us a better approximation than using than if we were to use 6 rectangles. Okay, now this is our fourth height for our fourth trapezoid. Okay, that's its base 1, base 2, and then that other leg, and then this. Okay, so speed up the video, guys, if you want. And then this last one here. Yeah, so trapezoids work pretty well for a rough estimate. You'll see something soon. Using a limit, we could get an even better estimate, which we will do tomorrow. Okay, so there's that. Now we just have to add up all the areas of these 6 trapezoids. So, and just be aware that for a trapezoid, h is equal to delta x. So in this case, delta x is just 1. All right, the change in x there is just 1. All right, so I have 6 trapezoids, so I'll go T1, T2, T3, T4, T5, T6. All right, and the information we need to use this formula, we'll put we'll multiply everything by 1/2 at the end, because that's never going to change. But what's really important is the height in base 1 and base 2 for each trapezoid. So here, the height, remember, is delta x. For rectangles, the base would be delta x, but for trapezoids, the height is delta x. And it's just 1 all the way down the line. And then we need the sum of the bases. Well, this is nice because they already gave us the coordinates of all of the endpoints that we're using. All right, so for the first trapezoid, base 1 plus base 2 is 6 plus 3, which is 9. For the second trapezoid, we get 3 plus 3, which is 6. I'm going to skip writing the smaller numbers. I'll just give you the sum in the end. But listen to my voice so you know what I'm doing. For the third trapezoid, the bases are 3 and 4, so we got 7. 3 and 4 again for the fourth trapezoid, right? Yep. Yep. For the fifth trapezoid, base 1 plus base 2 is 5, 3 and 2, and then 6 for that one. Oh, sorry. Okay, so the area sum is going to be 1/2, and just like we were doing, I mean, for each trapezoid, for each individual trapezoid, you'd go 1/2 times 1 times this, 1/2 times 1 times that, 1/2 times 1 times that. But you don't have to do it like that. Since you're multiplying every term of the sum by 1/2 and every term of the sum by 1, you could just factor out 1/2 and factor out 1, and then just add all of the base 1 plus base 2's together. So we're going to have 1/2, 1, not really necessary to write. And then if you add those all together, I got 40. Okay, so 20. And a pretty good estimate, as you can see, it's pretty close to the curve itself. Now this next part, guys, this is just notation here, okay, so don't overthink this. I'm just going to introduce some notation. It's going to look weird, but it's just like a language. It's like when you're learning a language, why do, in Spain they call a lake lago or something. I don't know. That's a stupid analogy, but it's like this is just language here. So express the shaded area as a definite integral. Okay, so we've got this shaded area. We don't have trapezoids or rectangles approximating this area. This is the exact area under this curve here. And that's what's called a definite integral. So please write this down. A definite integral gives the exact area. It is a Riemann sum using infinitely many rectangles. Okay, and we'll talk about this more tomorrow. But if you imagined adding infinitely many rectangles here, you'd have to take a limit to do it, which we'll do tomorrow. You would get the exact area under a curve. And the way that you write it is just like this is just notation. I'm going to take the function, I'm going to wrap it in parentheses, and very often they won't wrap it in parentheses, which is fine, but I think to get used to the notation, it's a good idea. You wrap it in parentheses. Now, you ask yourself, what's the interval that we are taking the area on? It is from 1 to 6. So what you do is this. You do sort of like an elongated S, that's an integral symbol, and then the endpoints of the interval go on the ends of the symbol there. All right, and then at the very end, you put a dx. All right, and this dx, it's just language, it's just notation. It doesn't change the problem if you left it out, but we want to keep it in there because you'll see in the future it sort of behaves like an algebraic element, and it was designed to behave that way. So that's what you do. You write the function, and then you got to put these you got to wrap it with these two things. All right, and what this means, the S came from an infinite sum. Okay, because what a definite integral is it's an infinite sum. So it's a sum of infinitely many rectangles over that interval underneath this function. Okay, and the dx actually stands for delta x. That's where the language came from. Okay, so there's that, guys. So yeah, that's it. Okay, this is how you say in the language of calculus the exact area under that curve. That's how you say it. All right. Okay, and the way it's read is the integral from 1 to 6 of this function. All right, that's how it would be read in words. Okay, so here we're not going to do this part. We have one more example. We're not going to do that. But we've got this. Approximate the integral using the trapezoid rule in 4 subintervals. So let's just write, okay, in language, this thing here is the integral from 0 to 1 of, we'll say f of x equals x squared plus 1. All right, so that's how you would read that. Okay, in the future, I think I should ask you to read that to me a lot. But this is the integral from 0 to 1 of x squared plus 1. And you don't have to read the dx. You don't have to read that. Okay, and what is this? This is equal to the exact area under f of x, which is equal to that, on 0 to 1, all right? Now, we are not going to find the exact area. We're going to approximate it using the trapezoid rule in 4 subintervals, okay? So first, let me find delta x. Delta x is going to be 1 minus 0, because that's the length of our interval. But then we want 4 subintervals, so you divide by 4. So 1 over 4. And remember, delta x, this is going to be the height of all of our trapezoids. Okay, it would be helpful to draw a picture. All right, so x squared plus 1, that's a parabola. We are looking at it from 0 to 1, and its y-intercept is going to be up here, so I'm going to draw it like that. All right, leave yourself a lot of room. We'll say that this is 0. We'll say that this is 1. Okay, so 4 subintervals. All right. So delta x is a fourth, so here is a fourth. Here is a half. Here is 3/4. Okay, guys, so we're just going to draw the trapezoids. So here is the first height. Okay, and then I'll get the bases by going like that. So there's the first trapezoid. Second trapezoid, there's the height. Already had that base. Now I need that one. And then this is the third trapezoid. Already had that base. There's that one. Fourth trapezoid. There's that base. And then you just connect the other leg. Okay? And then I'm just going to do the same thing that we did on the front. Okay, so we've got 4 this time. So trapezoid 1, trapezoid 2, trapezoid 3, trapezoid 4. We're almost done, guys. Okay, so the height is delta x, and that's a fourth all the way down. And then we need base 1 plus base 2, and then we'll just do 1/2 times the height times the base 1s plus base 2s added up. Okay, so I already figured them out in my calculator. So let's do this for your notes, okay? The coordinates of this point here are 0, 1. The coordinates of that point there are 1/4 and 17/16. All right, this one here is a half, and then 5/4. And I hope you know this, but if you don't, I'm getting the y-coordinate by just plugging the x-coordinate into the function that we're finding the area under. And then this is 3/4, 25/16. That's that coordinate. And then this one here is 1, 2. All right. So yeah, I just got the heights from the y-coordinates. Or not the heights, I'm sorry, the bases. So the bases of each trapezoid are just the y-coordinates on either end. All right. So for the first trapezoid, we had to do 1 plus 17/16. And then for the second trapezoid, 17/16 plus 5/4. Notice base 2 of the previous trapezoid is base 1 of the next one. So then this is 5/4 plus 25/16. and then 25 over 16 plus 2. All right, so now let's do the area sum. The area sum, so I'm multiplying, so for each trapezoid we got to do 1/2 times 1/4 times base 1 plus base 2. So since each term will have a 1/2 times 1/4, I'm just factoring them out. So we'll have 1/2 times 1/4, and then add all of the base 1s plus base 2s up. I did it already. I got 43 over 4. And then when you do this out, you get approximately 1.34375. All right, so now let's just practice with our language, our written language of calculus. So I'm going to say, therefore, the integral from 0 to 1 of x squared plus 1 dx, oh, I guess maybe you can read the dx, is approximately 1.34375. Not exactly, it's approximate, okay? To find the exact area, we would have to take a limit. And just one more thing, do this with me, please. Your calculator, I just want to show you the power of your calculator. Your calculator will actually do the limit. So let's see how good our approximation with trapezoids was. Because it is not very many trapezoids. 4 trapezoids is not very many. So you might think that's not going to give us a good approximation. So let me show you how to do something. Math 9 is going to be very useful for the rest of the year. It will compute a definite integral for you. And remember, a definite integral is just the exact area under a curve on a given interval. So you just type it in exactly as it appears. Okay, this is a universal language here. Okay, that's why your calculator knows the language. From 0 to 1, okay, so the integral from 0 to 1 of x squared plus 1. I guess you can read the dx. Often they don't. And then you hit enter. And this was really not bad. So that's the power of trapezoids, guys. If we did a rectangular approximation, it would not be this close. But that's pretty good. That's what we got with the trapezoids. And this is the exact area here. Okay, so not bad at all. Your homework, just to reiterate, is page 6, number 5. It's one like the one that we just did. And guys, try to do it the way that I did, okay? Like, try to mimic exactly all of this. To be honest, you know, if you just like drew a little picture, you know, had your estimate, that would be good. But we really want to practice with this language. Okay, so if I were you, it's going to be the most helpful if you write, you know, similar things to everything that I did. Okay, that's really going to show your thinking, and it will solidify the process in your mind. Alrighty, guys, I will see you tomorrow. Bye-bye.